Topic for today and for this week is forecasting. There are many techniques for forecasting, and we will not go through all of them, but there's only one theory, and we will go through the theory of what forecasting means. We will go through classical techniques for forecasting that are based on filters and time series. Those techniques are typically complemented with other techniques that are based on machine learning, which we will not see in this course because it's a topic of its own. However, the theory that we will do about what forecasting means and a number of other things that we'll discuss a bit later, they apply to all techniques, whether you use the linear time series methods or not. Linear time series is section 8 of this slide. So what we will do now, in some sense, applies to any technique you might use. So as you see here, forecasting is a bit of magic. Of course, there's only one thing that is certain in the laws of physics, is that the arrow of time goes in only one direction. So it's impossible to know what will happen tomorrow. So forecasting, in some sense, is going to be a risky exercise, and as some people say, it's easier to predict after the fact than before. So that's the first thing to remember. So if somebody pretends they have a new deep neural network system that will predict the future, of course, this will be true only with some accuracy. There are typical cases in the context of computer and communication systems where forecasting is very useful. For example, if you are running a data center for Infomaniac or Google or whoever, it's very likely that the load that you're receiving is not stationary. If your data center is not having trouble, it's probably increasing. Therefore, you need to reason about when do you need to buy new equipment. Remember Joe's and his small workshop at the beginning. He was wondering, do I need new servers? Do I need new access shops? At larger scales, you have, of course, more radical problems. And the step you do to answer such questions is, of course, to do some forecasting. So that's a very classical use of forecasting, where you want to be able to have some idea about the intensity of the load sometime in the future, because you need to plan deployment and investment. And there are zillions of other cases where forecasting is important. One of them is in a radically different context, in the context of renewable energy. If you have solar panels on your roof, then the amount of energy you will have tomorrow can be forecast if you have a weather forecast, for example. And therefore, how much you will need to buy tomorrow, if you're a big plant and you need to buy explicitly by going to the market, depends on the forecast here. In the lab, we'll do a forecasting exercise that is inspired by this, where your job will be to assume in a not so remote future, EPFL will not do like today, but buy energy by paying whatever is consumed, but has to go to the market to decide what to buy tomorrow or the day after. Then we need to do a forecast of EPFL's consumption. EPFL is a very modest producer. You see solar panels on the roof, but they're very small compared to the power that's consumed. So we have a time series of the power consumed over a number of hours. And your job will be to forecast sometime in the future of the trace that we have, the consumed energy. And we'll do a small contest, and the best forecast will have a smaller one. But to do the best forecast, we need to, of course, forecast what can be forecast, which is typically the exploitation of trends, seasonalities, things that are deterministic in your system. So one way to view a good forecast is to remove what is random from what is deterministic. Even something random may have an average point that's fairly easy to determine. So you may decide that something is between 2 and 3, so the average is 2.5 if you want. This 2.5 might be something fairly easy to forecast. This is called a point forecast. Very often that's the only thing that is done. But of course, we want a bit more, as you can guess from all the things we've done before. We want also to give uncertainty levels. Not just say, I predict that tomorrow we will use so many megawatt hour between 10 and 11, but I want also to be able to have error bounds on that, because the error I'm doing if I'm below or above the value might be very different. Things are usually nonlinear. If you undershoot, probably nothing bad happens. If you overshoot, you may need to pay very large penalty. So a forecast that doesn't have uncertainty intervals is practically unusable. Right? You want to quantify the uncertainty you have about the forecast. That's what we will discuss, how to remove deterministic components and how to produce uncertainty bounds. So a few definitions. What is uncertainty bounds? Well, I mentioned a point forecast. One way to think of a forecast is to assume that we have a process, y1, yt, that typically we have observed up to time t, and we want to say something at time t plus L. L is the forecast horizon. So if we're interested in a fixed L, a full forecast would mean, strictly speaking, the conditional distribution of yt plus L given y1, yt. That's, I would say, the mathematician's definition of forecasting, which is very often when we do practical things is a bit forgotten, but that's an important thing to remember. Things in the future are uncertain. In the best case, we're able to interpret the future as the realization of a random process. If we are able to make sense of this, to somehow capture the parameters or the structure of this random process, in this case, forecasting simply means being able to say something about the future given what we have observed. In probabilistic terms, the information is related, the concept of information is related to or is quasi the same as that of conditional distribution. So we'll come back to that. That's a useful interpretation for computing confidence in prediction intervals. A point forecast is just one point. So once I've recognized that yt plus L is something random, if I give only one point, I can give the mean or the median or something more complicated if it's a multidimensional. Any measure of centrality, typically mean, median, or combinations of that. For example, if we take the mean of the conditional distribution is called the conditional expectation. And the traditional notation is this one. The conditional expectation of yt plus L given y1, yt, which I write here y hat of t. Y hat to say it's a forecast. Index t means it's done at time t, based on all the information I have at time t. And L means L steps ahead in the future. Right. What is hidden in this thing, when I say expectation, there is something hidden. In order to compute an expectation, I need to have a probabilistic model of things. So what is hidden here and assumed is that I'm able to make sense of what expectation means. One way is to be able to fit a model to the system, and therefore, at least in theory, being able to compute it. A prediction interval is a definition we've already seen. A prediction interval, AB, is something that depends on y1, yt, so it's a function of all the data we have observed, such that the probability that the next point we want to forecast is between those bounds, given what we have observed, is at least some confidence level, typically 95%. Here. Let us start with very simple methods, which are very often used. The fitting of them may require complicated method, but the principle is very easy to understand. So the simplest method is the use of model fitting, what we just did last week. It's called regression methods. Here is an example. Here I have a time series, which is the internet traffic observed by periods of 90 minutes over a link of a provider. This is here US Sprint coast-to-coast link. And here, it's a very classical example. Why do we want to do forecasts? Where we're renting or either we own or we rent that capacity, but in either case, we want to use exactly the capacity we need. If the link is very little utilized, which happens at those periods, which are probably the middle of the night, then we are able to resell that capacity for something else, for data centers to do backup or for providing other systems. So as you can imagine, any large data infrastructure has that kind of behavior and would like to be able to predict things. Here, there's something very easy to predict. It is that there is a daily pattern. So 1 point here corresponds to 90 minutes. So there are 16 points per day, and one period of this, or quasi-period of this system, corresponds to 1 day. I mentioned at the beginning, one easy thing we want to do when we do a forecast is to remove the things that are deterministic. So day and night is something very deterministic. So one very first and easy things, a low-hanging fruit for forecast here, is to exploit this seasonality. One way to do it, I would say the signal processing way, is to say I fit a periodic function to this system. And since I am here for a minute signal processing person, periodic function means trigonometric function. So cosine with a phase, which means a linear combination of sine and cosine with the same period. And this period here corresponds to the fact that the period is 16 time units, so 2 pi over 16 here. Why sine or cosine? Well, in the context of data traffic, that might be a bit weird. In the context of physical systems, that's very often the simplest periodic function. But that is very often done. I'm not saying it's the best forecast, but if we apply this, we're saying my model of my data is it is a constant plus a sine function plus noise. And the period is known. So that model has 1, 2, 3 parameters plus noise. If I assume for simplicity that the noise is IID Gaussian with the same variance, then we are back to where we were last week. It's in fact a linear model with respect to the parameters, because the parameters are those 3 big numbers here. So you see yt depends linearly on them. Therefore, all the methods we've seen for linear regression model apply. We write the X matrix that will have the sine and cosine, and I can fit the model up to some time. Here I stop at this data point, and I can fit and obtain those values here. Right. And incidentally, I will also have an estimate of sigma. Once I have the model, one easy thing I can do to compute a forecast is to say, well, I believe in this. I believe yt is equal to that plus epsilon t, that is sigma square variance, a Gaussian with variance sigma square. This is what I fitted to the past, and then I'm putting an act of faith. I believe it will be true in the future, at least on the horizon where I predict. So given that, I can easily compute what is the conditional distribution of yt plus L given yt. What is it? Well, first let us write what yt plus L is. Yt plus L is the same as this, where we replace t by t plus L. So those are all big constants with respect to randomness, plus epsilon t plus L here. Right? And the conditional distribution. So forget about the conditional distribution. This is the equation for yt plus L. I'm saying yt plus L is a big constant, this one here, plus a random epsilon t plus L. I'm saying something else. I'm saying the conditional distribution of yt plus L is given by this. Yt plus L is equal to this epsilon plus a constant. Now the question is, what is the conditional distribution of this conditional to everything up to time t? Having observed everything up to time t, what can I say about this expression? Well, in my model, I assume that the epsilons are independent of each other. So having observed everything up to time t gives me no information on epsilon t plus L. So the conditional distribution of epsilon t plus L plus a constant is the same as the distribution, the unconditional distribution. So in terms of conditional distribution, I can say the distribution of yt plus L is the same as if I would write this thing here, with the conditional distribution of epsilon t plus L still is the same. And this is because of the IID assumption I made. So that is the first step, which is easy once we know how to take those concepts. Then how can I compute coverage interval? Well, first, how can I compute a point prediction? Well, the point prediction is, how can I predict this quantity? What is my best prediction for epsilon t plus L? If you have to give only one value, what do you predict? Zero. It's zero mean. So if you predict it by the mean, in average it's zero. So if I have no information, I will say zero. So a point prediction is obtained by setting this to zero. This is what we obtain here. The point prediction at time t plus L, in general, if I have a linear regression model, we simply apply the model by setting the noise to zero if we believe that the noise is IID with zero mean. This is what I did in this curve here. So this is a zoom of the right part here that I want to predict. So the black part is the black part that was here, but zoomed. So you see it's periodic, but not completely regular. And now the prediction is the red curve that is given here. This is exactly a sine function here. Of course, my model is giving a sine function. In blue, with circles, is the realization that I didn't know at the time I did the prediction, but that was revealed later, and this is what we have here. I can do a bit more. I can find a 95% prediction interval, because if I come back to what I have here, if I need to give a 95% coverage interval of this, which is now non-random, plus this, all I need is a 95% coverage of this. Epsilon is this distribution, so with 95% probability, it is between those famous numbers we've seen many times, plus or minus 196 times sigma. So a 95% prediction interval is the predicted value plus or minus 196 sigma. My sigma is known. This is what I put here. Those are the red dotted lines. And we see that it's not a bad forecast because that's a 95% confident prediction intervals, which means out of 20 points, 19 should be within this interval. That's what 95% prediction interval means. And we're close to that. We see that all here there are 24 points, all except 3 are inside the interval. So it's not a bad prediction interval. We could stop there. We could see, okay, this is all about forecasting. Once we understand what we do, the problem is to do a model fitting. Still, there's a number of secondary questions we need to address and a few techniques that will simplify our work, even on a simple example like this one here. Let's examine, for example, the model we used for illustrating model fitting last week. We had seen that the best model for the virus growth is to look at the log scale, and we found that the best model was, or one of the possible reasonable model, was to assume that the log of the infected population satisfies this linear equation with the noise being IID Laplace. Right? So if we believe in this model, then we have exactly the same thing. Those noises terms are independent. So a 95% prediction interval is obtained by finding a 95 coverage interval for Laplace, for the Laplace distribution, which corresponds to finding a 97.5% quantile of the Laplace distribution, because it's symmetric. We want to have the left and the right part, which is easy to compute. And I don't do it now, but this is a small homework exercise to compute that in closed form with the exponential function. So this is the 95% prediction interval. If I want a point prediction, I could simply set the noise to 0 and obtain this value here. And then if I go back to the original data, take the exponential of that, y hat t plus L is the exponential of the log. So the log is between the predicted value and plus or minus eta. So when I take the prediction, I obtain this interval here, which will be slightly asymmetric because we have multiplied now instead of adding the uncertainty. And this is what I did. In log scale, in fact, the prediction here simply means continuing the straight line, and any point here is my predicted value. And the prediction interval is given by the length here. In log scale, you see it's not very large, and it's compatible with the distance we see with respect to the line. In natural scale, we see that, of course, the interval is increasing here. The prediction interval we would have, therefore, at time 25 is somewhere between 20,000 and 50,000. You see the difference already with the prediction interval. Here, there's an example where it's fairly simple, so I could really do the exercise of trying to have a robust statement. I have done a robust model fitting. I've examined various ways of fitting the model, and I took one that seemed more realistic than others, like the least square. That's the obvious thing that we would be tempted to do. This one is better. And we saw that we can do a point prediction at this time, but we see that the uncertainty about the point prediction, if we take the most natural model, is very large. Which makes sense. If I have exponential growth, and there is some uncertainty about the line here, of course, when things get very large, in natural scale, the uncertainty will also be very large. But that's something that's often forgotten. That's something you, as performance-educated people, should not do. So next time you do a forecast, give at least some approximate idea about what is the uncertainty you have about your forecast. Otherwise, you're just cheating, right? Or you're just giving useless information here. Small quiz about this example. So we have some variations around B and D. So, is A true, right? So, well, of course, this is a contorted quiz. I mean, how could I use such a quiz? So, yeah, if A is true. If B is true, it means that A is true. Okay, so let's discuss A. The width of the prediction interval is constant and equal to 2/196 sigma. The answer is yes. This is how we did for this simple model. We assume that the model is the periodic function plus noise, and the noise terms are all independent. And we find a coverage interval by taking this, which corresponds to the 95% coverage interval, symmetric, for a Gaussian distribution. So A is true. Is B true? Well, is sigma is the root mean square of the residuals up to time t? Yes, we saw this is a property of least square. When we do least square fitting, in fact, sigma square, an estimate of sigma square, is exactly the average of the square of the error terms. Sigma is also the root mean square of the forecast errors. This is less obvious, but this is true also. And to see why, it's just sufficient to have the formula under your eyes. If we believe in this model, and if we apply this model backwards in the past, then an interesting feature of this model is that the term that is constant, that doesn't have a random variable, is also the forecast we will do if we stop everything before time t. So this, in particular, if we forecast yt at time t minus 1, epsilon t is the forecast error. So there is a whole class of models where we can interpret the random part as, in fact, a forecast error. Kalman filters are doing that all the time. Kalman filters are a special case of this, for example. So it is also the forecast error in some sense. So it makes sense then to assume that when we use the method of model fitting that has been shown, in fact, what we're assuming is that the forecast errors remain the same. And if we have estimated over the past, those are the forecast error bounds we also put into the future, which sort of seems consistent. Nonetheless, it's not always the best forecast methods. We will see different ones. But for the time being, that's all we can say. Of course, when I explained all of this, I put under the carpet an embarrassing question, which is, how about the estimation error? I have observed a few hundred points. Based on that, I estimate my model. And then I treat this model as, okay, now it's fixed. That's the truth given by God, who in a special channel informed me of the real truth, and now I can say things about the future. But in reality, the model I have obtained is estimated from the data. So there is some uncertainty about the model parameters. That's the topic of what we've done in the previous weeks. Quantify this uncertainty is called finding confidence intervals for the estimates. So we know, for example, the virus growth rate is not known with certainty. There is some uncertainty about the slope. So what I did, I treated the slope as constant and did a prediction for the future. So I was cheating. So let's discuss that. Is this cheating important or not? Here. Well, let's take a very, very simple example to understand. Assume we observe some data xn that is more or less a constant plus noise. So the simplest model. Of course, we don't do forecasts for such simple models, but that will help us understand. So the model is x is a constant plus noise. And assume we want to forecast n plus 1, xn plus 1. If we ignore the estimation uncertainty, we take our estimated value, mu hat, and we say, this is my prediction interval. Mu hat plus or minus 196, my estimation of sigma, if we ignore estimation uncertainty. Sorry, the point prediction for n plus 1 is simply mu hat. Now, even the point prediction itself we know is a bit uncertain. This is the confidence interval we have for the true mean, the true value of mu, given what we have observed. And if we ignore the estimation uncertainty, use the formula we have, mu hat plus or minus 196 sigma hat. That's simple. It is possible in this simple example to compute exactly what impact this uncertainty has about the forecast. So this point mu is itself unknown. Sigma is also a bit unknown. So if we want to say something about the future, all of this uncertainty will add up. It will add up in a nonlinear way. For this very simple example, there is a simple theorem that says if we have a sequence of points that is Gaussian with an unknown mean mu and unknown variance sigma square, and we want to forecast xn plus 1. Right? Then we know exactly a forecast interval. We know that it is given by this formula, which is interesting to observe. So the prediction interval, which means a forecast interval, is equal to my estimation plus eta, which is almost 196, but not exactly, is obtained from the student distribution, times square root of 1 plus 1 over n. In the formula I had before, I had almost eta here, and I had square root of 1. I multiplied sigma by 1. The true value would be square root of 1 plus 1 over n. This is how they add up here. So if we would apply this to the previous example, where I have, for example, 100 data points, the estimation uncertainty would be 199 instead of 196. So 198 is because the eta comes from the student distribution, and 199 would come because we have square root of 1 plus 1 over n instead of 1. So perhaps here the take-home message is 100 is not a very large number. The take-home message is, well, the prediction interval is largely due to sigma and very little due to the uncertainty about mu. So the estimation error typically adds up much less here. There is a general formula if we do a linear regression model, like I did for all the examples I presented so far. So with a bit more complexity, we can find exactly an exact prediction interval. It's very much in the vein of the things we've seen before. We need to compute the G matrix that comes from the X and the K, etc. I'll skip the details and I show how I applied them to the example we gave before. here I'm zooming on the end of the prediction interval, so I have a few hundred data points in the past, and I predict the next 24 points here. And I'm showing in red the point forecast. In light green is the uncertainty about the mean. So it's the uncertainty about this point forecast, which practically is not very interesting, but just in terms of illustration. The red dotted lines and the green dotted lines are the two lines we obtain when we apply the previous theorem that factors in all the uncertainty, the interval due to the prediction error, plus the fact that the sigma and the mu themselves are a bit unknown. And we see here it's nonlinear, because we see the green and the red dotted lines are quasi the same here. So because there is a square root in things, it's not that we take the same uncertainty about the mu and we add it here. No, it's a bit less. So here, in practice, what I did before, which consisted in ignoring the estimation uncertainty, which I shouldn't do if the point is just estimate the mu, then perhaps I should say something about this. But if I want a forecast interval, a prediction interval, I will see that whether I use green or red is the same. So I can, in practice, ignore the estimation uncertainty. So that's the take-home message from that. In practice, if you fit your model on a number of data, on a set of data which is much larger than the forecast horizon you want to do, then in practice you're very likely, or we believe that we will be very likely to be in a case like this, i.e. we can ignore the estimation uncertainty when we compute prediction intervals. Here, as an illustration case, I computed the prediction interval assuming my data set on which I estimate the model is very small. So I estimated on the same number of points over which I'm doing the prediction. I estimated over only 24 points, 1 day and a half. Very risky, right? I estimate tomorrow based on the history of today and half of yesterday. If I do that, then I see that the error bounds here start to be a bit more. So the uncertainty is so large about the value in the middle that they start showing up. But even then, they don't. If I would take the red instead of the green for the dotted lines, the error would not be very large, which confirms that this is a safe thing to do. Now, the bad news is having exact formulas where I can do this comparison is very rare. It's only in practically linear regression model with least square. But those are not always the best models. So the only thing we can do is believe in the fact that this will be true in general. Let's move on now to another important topic that is known, of course, in many other fields as well, which is called the overfitting problem. Has anybody heard of that before? Yes? What is the overfitting problem?
Like in learning, we overfit when the model learns exactly the trained data. So it's going to fit all the data we have in the train. And so basically also fits the noise, which will lead to worse result on general test.
Exactly. So if we have a model and we have a lot of parameters at our disposal to make the fitting, we can do a very, very exact fit over the past. But we know from learning theory that if we're too exact over the past, in fact, we might not have learned. We're just reproducing exactly the past, but we have not learned. It's what we do when we learn history from school. Then a completely autistic student could say, but what happened to the Romans? The Roman Empire collapsed one day. But doesn't mean the Soviet Empire should collapse, because the Soviet thing is not the Roman. Things are different. They don't use the same technology, the same ideology. So if you fit things too exactly, you don't generalize. Right? So that's the the trade-off between exactness and generalization. Of course, if you exaggerate in the other end, you have a very, very crude model, and your forecast might be bad because you don't capture the essential details. In the context of strictly forecasting, there are tools that we can use to avoid the overfitting model. We'll see that. But let's first examine in practice the overfitting model in this example here. Here, I could say, well, I'm fitting my data, which is the volume of data on a communication link. Here, I could fit them by periodic function to capture the daily pattern. But also, I know that traffic is growing. Right? I think in IT, we can only grow until we collapse, but we don't know how to be stationary. So if traffic is growing, which is not, of course, very visible at such a small time scale, but if you look at things very in detail or over a longer period, you will see there is a small growth which you could capture by a polynomial growth. It's not like exponential growth, but it still is growing, so I capture it with an exponential growth. So I could say a better model is a model that adds a polynomial term. Also, I've observed here that when I do the fitting with my sine function, I mean, obviously, those lines are not exactly sine functions. They are periodic, but they have a shape that is not exactly that of a sine function. From Fourier analysis, we know that any periodic function can be expanded, at least if we ignore the embarrassing convergence stories, but can be expanded as a sum of sine with frequencies that are multiple of the base frequency, harmonics. Right? So I add here more harmonics, which is h, to improve the model. So I did that here with a polynomial of degree 10, or of degree 10. So I have 11 parameters to fit here for the polynomial part, and with 2 harmonics, so 3 components in my periodic function. So you see, even that I'm not completely able to fit this peak here, but I have a shape that starts being more true to the irregularity of this here. There's a daily pattern, but it's not a pure sine like the tide. There is a plateau, there is a period of the day where there are 2 small peaks practically here. Here, this is the model I did before, I presented before, and this is the improved model. You see, this one fits better. Here, for example, I had 2 of those things that have been changed. So, I have a better fit here. Now, let me do the prediction for the second model. This is a prediction I find. This is the mean value, and this is the prediction interval. Of course, the prediction is ridiculous. It's predicting negative values, in fact, which is exactly the phenomenon you showed there. I was trying to mimic exactly things that were random here. So the fact that here there has been a small decrease due to whatever reason, and therefore I think it will decrease forever, and I'm choosing polynomial functions that have no physical explanation to relate them to what I'm doing, so I'm obtaining something that's completely bizarre. So that's an example of the overfitting model. I had a model that was very good or much better than a simple one to fit the past, but obviously it doesn't make sense. Right? It could make sense if the only thing to model is exactly this time series, but of course that's not the case. So the prediction power of this model is ridiculous here. So how to avoid overfitting? How do you do that in deep neural networks?
By having more data or a simpler model with regularization techniques.
Mm-hmm. So one of the methods that's classically used in machine learning, which we can apply here also, is to test the quality of what we're doing by reserving part of the data that is used for training for testing. What we want to do is predict. So we train the model, then we test its prediction ability on some data, which of course is not the one on which we've tested. And then if we have a class of models to choose from, we'll pick the one that is best by testing it in the field, in some sense. We can always do that. So I did that here by reserving some data for testing. For the model, for example, that has 2 harmonics, or 3 periodic components as a function of d, and I'm showing the prediction error. So I've reserved some data, so the last 24 data points, and I compute some integral of the prediction error, and we see that things don't get better when d increases. We see that the best d is for d equals 4. That's one possible method here. This method has the drawback that it requires to burn some of your training data, so you perhaps don't want to do it. In the context of time series forecasting, there is a more established method, which is called an information criterion, which in machine learning we could call a regularization term. When we do model fitting, the signal processing interpretation is we minimize or maximize the score of the fits by aggregating the errors. Here, we add to the score a penalty term, something that will avoid the overfitting problem here. So that's exactly what is explained here. So the score function for a parametric model is the log likelihood, or the likelihood, but very often the log likelihood. If we have Gaussian or Laplace noise, it's more convenient to reason with log. And the score, if we do just maximum likelihood estimation, is the log of the likelihood. The likelihood is usually 10 to the minus something, so we take minus the log likelihood, and then we want to minimize it here. And we have seen that if we have, for example, a homoskedastic model, homoskedastic means what? Yes, homoskedastic is one of those complicated words that people have invented in statistics to have things look more complicated than they are. It means the IID model with Gaussian noise and 0 sigma square. And homo means same, means the same sigma square for all data points, as opposed to a sigma square that might be affected by a weight, which would be called heteroskedastic. So the homoskedastic model will tell us that the score is n times the log likelihood plus a constant, and therefore, the maximum likelihood estimator is the one that reduces the aggregated noise. Well, that's as we saw in the past weeks. So to avoid overfitting, one way is to add this penalty term, which can be simply equal to the number of parameters, the dimension of the model to be fitted here. So the idea is if I have many, many parameters, then I will have a penalty that is larger. So the optimum will be something that is a good fit, the likelihood is good, but also has a number of terms that is not too large here. So this form here is called Akaike's information criterion, which is equal to, for example, if we have a linear model with a homoskedastic model, it will be 2n log of sigma hat plus 2p, where p is the number of parameters, the dimension of the parameter we're fitting, plus a constant here. This is not just a pure ad hoc thing. There is an interpretation that's explained in the lecture notes that I will not give in detail, but we can interpret what this criterion means. This value here can be interpreted as in average, it's the amount of information that's required to describe a new hypothetical sample when we estimate the model from one sample. So what does that mean? I have seen some data, and somebody proposes to me a model. We've seen 2 models, for example, for my time series, depending on whether there are many harmonics or not. So I can have multiple models for the data. The Akaike information criterion is capturing the amount of compression I'm able to do if I have to code to compress maximally a new independent realization of what I've seen. So I've seen some random x. I estimated with the model. If I have a good model, if somebody gives me a new x, then I'm able to compress it more because I know already the law of it. For example, if it's increasing or decreasing, I can capture of this, and the only thing I need to describe is the noise term, the unpredictable terms. Right? So if I have predicted very well the model, the only thing I need to give to you is the epsilons. And then I will need to code the epsilons, and it will give me a number of bits to code that. Right? If somebody has a poor model, for example, if you're telling me this is an exponential random variable, when in reality I will give you a sequence of 10 samples that will be Gaussian, then your prediction will be very poor. So we'll have large deviations very often, so I will need more bits to describe it. So in some sense, Akaike's information criteria is capturing exactly whether we've obtained all the information we wanted from this sample. And then we believe the future will be like the past, therefore that's the best we can do here. There are other regularization terms. One of them is more ad hoc, is called Bayesian information criterion. Instead of taking 2p, we take 2p times log n, where n is the number of data sample. So this is an ad hoc thing. So it penalizes more a large model dimension when the sample size is large as well. Some people believe it's a bit better than Akaike's information criteria, even though it doesn't have this reassuring statistical interpretation. Let's check this, because these are all theories, so let's apply them in practice to my forecasting example. Here, I'm showing d is the number of degrees of my polynomial, so I have only up to linear trend here, and h is the number of harmonics, h minus 1 is the number of harmonics in my fitting, and I'm showing the prediction error using reserved data and versus the estimation error, and we see the best model is for 2, h equal 2, and I can do now the similar thing by combining those two, by computing either of those information criterion. In blue is Akaike's information criterion, in red is the BIC. And now the difference with the two, here I need to test my prediction on some data. Here I'm only fitting the model. I'm not burning any data for doing a test. And we see here that there is a fairly good coincidence. We find that it's minimum for 2, for h equal 2. It's practically flat after by the principle of parsimony. If you have a model that is larger and have the same criteria, you should take the smaller one, the smaller order model, because they have the same prediction power, and this one is simpler. So, take-home message, if here I'm trying to see how many harmonics do I need, the Akaike information criteria is good. If I apply that to the, yes?
So the estimation error is the error in the parameters?
No, that's the fitting error, that's the sigma. That's the fitting error, that's the estimation of sigma. So if I have a model that has more parameters, I'm able to better fit my signal, my trace, and therefore I have a smaller error. And this will always increase, right? The more, because it's an optimization problem that we're solving. If I increase the number of parameters, I'm increasing the space over which I optimize. So the previous solution I had before is in the space that I have when I augment. So the more parameters I have, the better the fit will be. There's no limit. Of course, the limit is at some point where we have as many parameters as data points. We have reproduced exactly the time series we have. Now here, I do the opposite. I fix the number of harmonics to 2, and I vary the degree of the polynomial. And we see that the prediction error becomes very bad when the degree increases, and the best d is 4. But we see that the Akaike's information criterion is not exactly helping, because it's still giving, saying that, so if we compare to here, it was minimum at the good value, but here not at all, right? It's minimum at a value which is not good at all, right? In fact, where the prediction error is fairly large here. So take-home message, well, Akaike's information criteria, or other criteria, work well if your model has some affinity with your data, if the model makes sense for the data that you're studying. You're trying to fit random models like a polynomial is, because we think of a polynomial as perhaps something like this, right? Or something like this, right? Growth. But that's not the reality of polynomials, right? Polynomials are also like this, right? So when you fit a polynomial, in fact, if you don't put limits, constraints on the parameters of the polynomial, you don't know exactly what function you're obtaining. You might be obtaining a function that dives to the seller very quickly, like happened here. So take-home message is information criteria are not able to identify models that are not in a good class. If the models are completely random and bizarre, the information criteria will not help you here. In particular, if the value of the model in the future has nothing to do with the value of the model now, which is what happens for polynomial, not for periodic terms. Therefore, Akaike's information was able to give you the best order for the number of harmonics, but not for the degree of the polynomial. One little quiz to conclude. And of course, the correct answer is A. This was just a wake-up question.